So let's take a look at the Cretaceous. So here, as you can see by the paleogeographic map, sea level was definitely really high during the Cretaceous. And that is question number 38, right? Very, very high during the Cretaceous. You can see that, remember, in the Triassic, the seaway was just out here, right, because we still had continents attached over here, and Europe was still up here. Well, as these continents started to separate off, remember, in the Jurassic, we started to get more coverage, and then in the Cretaceous, you can see the whole middle portion of Laurentia is definitely completely covered again, right, with water. Now, 38A, there is definitely one type of deposit that's very characteristic for the Cretaceous, and that's going to be chalk. And 38B, what creates these deposits are coccolithophores. And coccolithophores are these microscopic organisms, and their shells is essentially made up of calcite. So when they get compressed, they form chalk, which is really quite impressive when you start thinking about formations like the White Cliffs of Dover, where you've got several hundred meters high of chalk, and you realize that it's just these little tiny microorganisms that are making that. So Cretaceous gets its name from this chalk deposit. So Creta in Latin means chalk, so that's where we get the Cretaceous from. Now, question 39, out in the Atlantic, remember what we've watched now is in the Triassic we start to see Africa rift off of Laurentia, and it just continued through to the Jurassic. So now by the time we get to the Cretaceous, we have actual ocean floor now sitting in between these two continents. So what's going to happen now is sediment from the Appalachians is going to start getting washed out into the ocean to get deposited. Now, we saw it on the land side, right? That's what we call our clastic wedge. But on the ocean side, we're going to get the same thing. So because of the weight of that sediment, okay, for 39, we start to see the Atlantic coastal plain start to sink. So what we see here is the original edge of the continent when Africa broke off. And now you can see we're starting to get lots of sediment, right? So in the Jurassic, we start developing, right, our continental shelf, right? So there's the shelf, right, the slope, and the rise. Okay? And then in the Cretaceous, we see even more sediment come on. So now you start to see that that grade of the slope starts to lessen out. And then today into the Cenozoic, you see the grade lessen even more. So what we're getting here is just all of the sediment that's washing out of the Appalachians is getting deposited out there, creating this really nice, pretty continental shelf deposit. And so question 39A, what this is forming is we're forming the continental margin. Right? So instead of having a cliff from where those two continents broke off, now we've got this nice, pretty continental margin. Off those margins, out on the continental shelf, we also start to see lots of reefs. Just like here in the Gulf states, we get lots of oyster reefs. Well, in that time, we didn't have so many oysters, but we had rudists. And rudists are similar to oysters, but they form reefs, just like those oysters do. And today, rudists are really important because those rudists are important sites of oil and gas formation. So now let's get back into the orogenies, right? So we have two more orogenies that are now about to occur with the Rocky Mountains. So we're moving into question number 40. Right, so we saw the Sonoma orogeny and the Nevadan orogeny, right? So remember, what we're seeing is these rocks are just getting so fragmented and so broken up that we're starting to see the transfer of stress move to the inland. So in the Cretaceous, number 40, 40A, we start to see our next orogeny, and that is the Seaver orogeny. Now, what's really impressive about the Seaver orogeny, so remember, here's where subduction is happening, right, way off the coast. Remember, right in here, we got the Sonoma orogeny, then the Nevadan orogeny. Well, what's happening here, 40B, what makes this really unique is as this area is getting pushed, right, so we're pushing this area against each other. Remember, these rocks are all broken up. So this transfer of stress gets really crazy. And it moves to the inside, and what happens in this area, this is where the Seaver orogeny happens, it physically compresses it and folds it like an accordion fan. So if you take a look down here, right here, these are what we call Seaver faults. So it's essentially, if you were to straighten this out, I think you can see by the way the colors are that this would be a nice flat layer, but you see it got broken, and these layers get stacked one on top of the other, on top of the other, on top of the other. Right? So they're just folding and breaking and stacking on top of each other. So that's what makes this unique, is that we are shortening the crust. And we're shortening the crust by 60 miles. That's what's really impressive to me. So if we were to stretch out this region, right, of the Rockies, North America would be 60 miles wider. Now, the very last orogeny that occurs, okay, for all of the Rockies, so this is 40C, is the Laramide orogeny. That is the very last one. So with the Laramide orogeny, now we're starting to see deformation happen the furthest inland. So this is a great picture. It kind of gives you an idea of what's going on here. So here, right, we have the Sonoma, here we have the Nevada orogeny, here we have the Seaver, and then on the very inside we have the Laramide orogeny. So that gives you a really good idea of how this transfer of stress has really moved to the inside of the continent. So again, what we're getting is we're getting subduction, right, off the coast, and because it's just pushing there, that transfer of stress is going on the inside. So this last orogeny, 40D, creates the Rocky Mountains, right, as we know them today. Now what's interesting about this is when the Rocky Mountains initially formed, they definitely weren't this high at all, right, as high as they are today. What's happening is the mountains are slowly starting to lose weight from all of the erosion that's occurring, which is making them lift up a little bit higher. So actually today, right, the Rocky Mountains are actually getting taller, right, than they were back in the Cretaceous. So for 40E, what I want you to realize here is that deformation switches inland. So the first orogeny happens on the coast, and the last orogeny happens on the interior of the continent, which is very backwards, right, to everything that we've seen so far. Now, we've seen, obviously, there's subduction occurring off on the west. So because we've got, because we have all these volcanoes, right, that are a result of that subduction, we're going to start to see some pretty cool rocks get deposited in the Foreland Basin. So this is 41. So the Foreland Basin, let me just go back to this picture, is going to be this area, right, that's in between these orogenies. So we're going to see these little basins of areas, right, that are between these mountainous regions start to collect deposits. And the first of the deposits that we're going to start to see is a volcanic ash bed, right, from all those volcanoes that are occurring out west. Now, volcanic ash over time doesn't stay ash. Remember, it turns into clay. So we call this bentonite, right? This is weathered volcanic ash. Now, the second rock type that we start to see get deposited in the Foreland Basin is a limestone. Very specifically, we see the Niobrara Formation get deposited. And the Niobrara deposit is a really important formation because this is where we get most of our pterosaurs, right, our flying reptiles. So they're flying over this inland sea. Remember, this is a limestone, so this is definitely a reef. They're flying over this inland sea, and they're swooping down to catch these fish. And as they die, they're probably going to die in midair. So as they die in midair, right, their bodies kind of fall down to the bottom of the ocean floor, and they get preserved in this limestone. So what's really neat about this, right, is we get nice, full pterosaur fossils as a result. Now, as we get to the end of the Cretaceous, question 42, we see something very different happen. Remember, the Mesozoic is characterized as warm. We saw the temperatures warm through the Triassic, warm through the Jurassic, and they're super hot by the time we get to the Cretaceous. However, at the end of the Cretaceous, it's a very different story. The climate becomes very cold. It becomes cool towards the end of the Cretaceous. So there are four things that we can see that show us that the climate changes, right? This is 42A. First, we see the regression of the epicontinental seas, right? That's telling us that our glaciers are getting big on the poles and those epicontinental seaways are regressing. Matter of fact, at the end of the Cretaceous, that's the last time we see ocean on our continent. Right? The ocean disappears off Laurentia, and we haven't seen it again since, right? You can today go drive your car to Colorado and you don't need a boat, right? So there's no more ocean there anymore. The second thing is we start to see with paleomagnetic data that Antarctica is starting to move onto the South Pole. Now it's important to realize that Australia is still connected to Antarctica at this time. So Antarctica is not the frozen tundra that we see today. It's not going to become that until we get to the Cretaceous, when we actually see Antarctica separate away from Australia. Now, number 3, we also start to see some changes in terrestrial plant populations. Basically, what we're starting to see are tropical plants decline in number and get reduced towards the pole, and then we start to see lots of hardier plants, right? Plants that can tolerate the cold weather become much more common throughout the fossil record. And then number 4, we also see with our oxygen isotope ratios that the climate is getting colder. This is something we're going to investigate more in Chapter 15 in the Cenozoic, but essentially what happens is we're going to look at some oxygen isotope ratios, and those ratios in certain amounts tell us the actual temperature, right, of the land. So we're going to see that this ratio that we see in the Cretaceous is telling us that things are definitely getting a lot cooler.